Hey guys, let's talk about a couple of features, networking features of Kubernetes. Now, let's start with advanced services because we already had discussion of, the basic services. Let's quickly move to advanced services and let's explore the IP strategy as it relates to services and communication between containers. If you uh, if you recall in the services lecture, wherein we discussed about pods, services, replication control, and labels, we learned that Kubernetes is using kubeproxy to determine the proper pod IP address and port serving each request. Now, behind the scenes, kubeproxy is actually using virtual IPs and IP tables to make all this magic work. kubeproxy now has two models, user space and IP tables. As of now, 1.2 IP table is the default mode. In both modes, kubeproxy is running on every host. Its first duty is to monitor the API from the Kubernetes master. Any updates to services will trigger an update to IP tables from kubeproxy. For example, when a new service is created, a virtual IP address is chosen and a rule in IP table is set, which will direct its traffic to kubeproxy via random port. Thus, we know how to have to capture service destined traffic on this node. Since kubeproxy is running on all nodes, we have cluster-wide resolution for the service VIP, short for virtual IP, which we use. Additionally, DNS record can point to this VIP as well. Now, in the user space mode, we have a hook created in IP table. Put the proxying of traffic is still handled by kubeproxy. The IP table rule is only sending traffic to the service entry in kubeproxy at this point. Once kubeproxy receives the traffic for a particular service, it must then forward it to pod in the services pool of candidates. It does things using a random port that was selected during service creation. Now you can refer to the following figure which you see on the screen right now for an overview of the flow. Since it is self-explanatory, I would not take much of your time to cover that up. Now it is also possible to always forward traffic from the same client IP to the same backend pod container using the session affinity element in your service definition. In the IP table mode, the pods are coded directly in the IP table rules. This removes the dependency on kubeproxy for actually proxying the traffic. The request will go straight to IP table and then on to the pod. This is faster and removes a possible point of failure. Readiness probe as we discussed earlier as well. Now, let's talk about external services. Now, in external services, we saw a few service examples. For testing and demonstration purposes, we wanted all the services to be externally accessible. This was configured by the type load balancer element in our service definition. The load balancer type creates an external load balancer on the cloud provider. We should note that support for external load balancer varies by provider, as does the implementation. In our case, we are using GC, so integration is pretty smooth. The only additional setup needed is to open firewall rules for the external service port. Let's dig a little deeper and do describe command on one of the services from the more on labels, which we discussed earlier. And the command is, as you can see at the top of the screen, kubectl JS labels. The following screenshot is the result of the preceding command, as you can see on the screen. In the output in the preceding figure, you will note several key elements. Our namespace is set to default type is load balancer, and we have the external IP listed under load balancer ingress. Further, we see endpoint, which shows us the IPs of the pods available to answer service requests. Moving on to internal services. Let's explore the other type of services we can deploy. First, by default, services are only internal facing. You can specify a type of cluster IP to achieve this, but of no type is defined. Cluster IP is the assumed type. Let's take a look at an example. Note the lack of the type element as you can see on the screen right now. Use this listing to create the service definition file. You will need a healthy version of the node-js RC. As you can see, the selector matches on the pods named node-js that our RC launched in the earlier lectures. We will create the service and then list the currently running service with a filter, as you can see here. Here I am pointing through my mouse cursor. The following screenshot, as you can see here, is the result of the preceding command. Now, as you can see, we have a new service but only one IP. Further, the IP address is not externally accessible. We won't be able to test the service from a web browser this time. However, we can use this handy kubectl1 execute command and attempt to connect from one of the other pods. You'll need node-js-pod running. Then you can execute the following command, as you can see here. This allows us to run a docker exec command, docker execute command, as we had shell in the node-js-pod container. It then hits the internal service URL, which forwards to any pods with a node.js label. Now, if all is well, you should get the raw HTML output back. So you successfully created an internal only service. This can be useful for backend services that you want to make available to other containers running in your cluster but not open to the world at large. Now, talking about custom load balancing. Now, a third type of service that K8s allows is the node port type. This type allows us to expose a service to the host or node minion on a specific port. In this way, we can use the IP address of any node and access our service on the assigned node port. Kubernetes will assign a node port by default in the range of 3000 to 32767, but you can also specify your own custom port. Now, in the example, node.js-service-node-port.yaml, we choose port 30001 as follows, as you can see on the screen right now. Now, once again, create this YAML definition file and create your service as follows. As you can see this screen, this command, the output should have a message like this. You will note a message about opening firewall ports similar to the external load balancer type. Node port is exposing your service externally using ports on the nodes. This could be useful if, for example, you want to use your own load balancer in front of the nodes. Let's make sure that we open these ports on GCP before we test our new service. From the GCE VM instance console, click on the details for any of your nodes. Then click on the network, which is usually default unless otherwise specified during creation. In firewall rules, we can add a rule by clicking on Add Firewall Rule. Now, create a rule like the one shown in the following figure. So, TCP is, again, as I said, 30001 on 0.0.0.0/0 IP range. So as you can see in this screenshot, we can now test our new service by opening a browser and using an IP address of node in your cluster. The format to test the new service is HTTP minion IP address colon node port. Finally, the latest version has added an external name type which maps a CNAME to the service. Okay, so let's take a pause here, and we will proceed with a few more networking related features in the next set of lectures. So thank you very much.